Right. Let us now move on to the next problem, problem number 16. So, let me read it out first. Two planets, P1 and P2, having masses M1 and M2, revolve around the Sun in elliptical orbits. So there are two planets, P1 and P2, of masses M1 and M2, which revolve around the Sun in elliptical orbits. So as we know from celestial mechanics, the Sun is always located at the foci of the elliptical orbit. So let's assume that the Sun is here somewhere. This is the foci orbit, and this is the center of the ellipse. And this A marks the length of the semi-major axis. Two planets of mass P1, M1 and M2 revolve around the Sun in elliptical orbits with time periods T1 and T2. Time periods T1 and T2 respectively. The minimum and maximum distances of planet P1 from the Sun are R and 3R respectively. So it says for planet P1, which has mass M1 and time period T1, has a maximum distance of 3R from the Sun, which means this distance is about 3R. And the minimum distance of R, then this must be R. Whereas for planet P2, these are 2R and 4R respectively. So for planet P2, these distances are 4R and this, not this distance, this is the same major axis. But the distance from the Sun, which is 4R, and the minimum distance is 2R. Assuming M1 and M2 are much smaller than the mass of the Sun, assuming M1 and M2 to be much smaller than the mass of the Sun, what is the magnitude of T2 by T1? So we need to basically find out the ratio of T2 over T1. Now, for this, we immediately recall Kepler's third law of planetary motion, which says T square is proportional to R cube, where R is supposed to be the radius of the orbit. In that case, it's assumed to be a circular orbit. Here, the orbit is elliptical, so we'll replace it with A cubed. And it said that M1 and M2 are much less than the mass of the Sun. Let's call this the mass of the Sun. Much less. M1 and M2 are much less than ms. So time period, if you recall, depends only on ms and A. So we don't have to worry about masses at all, the masses of the planets. All we need to worry about is finding A. Now let's call A to be A1 or M1. So here you see that we are given the maximum distance from the Sun and the minimum distance from the Sun. which would mean that twice of A1 is 3R plus R, 4R. Twice of A1 is 4R, gives you an A1 twice of R. Whereas for planet M2, twice of A2 gives us 4R plus 2R, 6 of R. 6 of R. A2 is 3 of R. So you see, there we have it. We have our values of A1 and A2. So now we know that T square is proportional to AQ, which means that T2 over T1 whole square will be equal to A2 over A1 whole cubed, and A2 over A1, 3R over 2R whole cubed, which is 3 over 2 whole cubed, which, so T2 over T1 comes up to be square root of 3 over 2 whole cubed. And if you look at the options given, one of the option is 3 by 2 over square root of 3 by 2, which is exactly what we have written. You decompose it into 3 by 2 whole square times 3 by 2, and the whole square comes out of the square root, and you have 3 by 2 over 2 by 10, which is our option is C. So our correct option for this answer is C. Our final answer is 3 by 2 over square root of 3 by 2. So that concludes our problem. Let us now move on to the next problem. Problem number 17. So this is an interference pattern problem. The problem states the intensity of the primary maximum in a two-slit interference pattern is given by I2. The intensity of the primary maximum in a two-slit interference pattern is given by I2. So two-slit interference pattern. Central maximum is I2. Central maximum is I2. And the intensity of primary maximum in three-slit interference. Three-slit interference pattern, I max is I3. Now, it is said that assuming far-field approximation, same slit parameters, and intensity of the incident light in both cases, I1 and I3 are related as. So you're assuming the intensity of the incident light in case 2 is the same as intensity of incident light in case 3. Far-field approximation and slit parameters are the same. So then how is I2 over I3 or related, or rather, how is I2 related to I3 now? In this case, we just need to recall one fact about the interference pattern. When you have an interference pattern, no matter how many number of slits, the intensity, the final intensity is always n squared times the incident intensity. where n is the number of slits. N is the number of slits. The intensity is always n squared times, which means that for I2 we'll have 2 squared times I intensity, and for I3 we'll have 3 squared times I intensity. That's all we need to solve this problem. And so therefore I2 over I3 would be simply 2 by 3 whole squared, or it's about 4 over 9, which means I2 is about 4 by 9 times I3. And according to the options given, this is option D. So I2 and I3 are related in the ratio of 4 of 9, 4:9. So this concludes our problem of interference pattern, and we can now move on to the next problem. Let's move on to the next problem. Problem number 18. Says a short rod of length L and negligible diameter lies along the optical axis of a concave mirror at a distance of 3 meters. A short rod of length L and negligible diameter lies along the optical axis of a concave mirror at a distance of 3 meters. The focal length of the mirror is 1 meter. So let me rather draw the picture so that we start seeing the problem. Start picturizing the problem. So this is a concave mirror, and let's assume this to be the principal axis. And it says that the focal length of the mirror is 1 meter. So let's assume this is the focal point, and this is the focal length. Twice of the focal length would be the radius of curvature, which is also 1 meter from here. Also 1 meter. And the rod is placed at a distance of 3 meters. At a distance of 3 meters. So this somewhere here, let's say the rod is placed. This distance is 3 meters. And it says that L, the length of the rod, is much less than 1 meter. So you can neglect the length of the rod, and L prime is the image somewhere, and L prime is the length of the image. We have to find out what is the ratio of L prime over L, or basically what is the magnification. So how to proceed with this problem? So if we recall the properties of a concave mirror, if you place an object between infinity, a distance somewhere between infinity and C, center of curvature, and an image is formed somewhere between the center of curvature and the focus. So in this case, we can, of course, we don't have to worry about locating the image at all, because we can simply use this formula, the very well-known formula. 1 over object distance plus 1 over image distance should be equal to 1 over focal length. And our object distance is 3 meters. Our image distance is unknown. Focal length is 1 meter. So image distance is given by 3.2 meters, which is about 1.5 meters, and as you see, 1.5 meters lies somewhere between the center of curvature and the focal point. And we need the magnification, which is the ratio of the image distance to object distance, and this is basically, well, if you ignore the sign, the sign, there is negative sign because the image is inverted. The image is inverted, so there is a negative sign, and it is the ratio of the image distance to the object distance. So that should give us about 1.5 times 1.5 divided by 3. That comes out to be about 1 by 2, or if we just ignore the sign, this should come out to be about half, or L prime should be equal to L by 2, which says that the image is actually diminished in this case. The image is diminished, and that is our option B. That concludes this problem. We can now start moving on to the next problem.